Hey guys, continuing on our merry way of respiration. We did glycolysis, we did transition steps. We now are in the Krebs cycle, still in the mitochondrion. Glycolysis takes place in the cytoplasm. Transition step, transition from cytoplasm into mitochondrion. Krebs cycle takes place in the matrix of the mitochondrion, which means inside the inner membrane. Like you remember when mitochondria has some outer membrane and inner membrane that is extremely indiginated. I'm going to do that really poorly, but that's it. And each of those invagination is called a cristae. Remember, the matrix being inside the inner membrane. This is where the Krebs cycle takes place. And as we did before, I'm going to just tell you about input and output first, and then we go through what you should know from the Krebs cycle. So first of all, let's address the elephant in the room. Why is it called Krebs cycle? Why would we call that Krebs cycle? Well, you guessed it. That's the old white man who actually found about it. So we have to name it after him. I don't know why, just the fact. It's just a name. Don't worry about it. Let's move on. So Krebs cycle, as I used to do for glycolysis and transition step, always start with output. If you think of the output first, you will understand the input. So the output of a Krebs cycle is 4 molecules of CO2, 2 ATP molecules, and then really important, that's the best step for that, 6 NADH, don't forget the little electrons, electron carrier, and 2 FADH2 with the electron carrier as well. Those molecules are highly revered in the respiration because they contain a lot of potential energy that will be used in the electron transport chain. Now that you think about that, well, what happened to acetyl-CoA? We started with acetyl-CoA, right? After transition step, we had acetyl-CoA coming in. So that's our input in the cycle. And acetyl-CoA is a 2-carbon molecules. This is 2 carbons here. And you go from 2 carbon molecules, or you have 2 of it, right? Because you come from 2 pyruvate. You have 2 of them, so it's 4 carbons, and here we have 4 CO2. Bingo, right? Now you realize when you see 4 CO2, you should think of 2 acetyl-CoA because acetyl is 2 carbon, so I get 4 carbon. I respect that. And then you continue to ATP, that means you have 2 ADP plus 2 phosphate group. 6 NADH, you have 6 NAD plus H plus, right? Plus 6 H plus. And you have 2 FADH2, you have 2 FAD plus actually 4 H plus in this case, because it's H2 here, right? So here you go. You have your input and output. Learn those. Learn your output. You can work your input because you remember acetyl-CoA from the transition step. And so you will remember that it's 2 carbon acetyl, so you need 2 acetyl-CoA to make 4 carbon to match the CO2 level here of 4 CO2. Okay, now let's move on to the cycle in itself. So when we talked about the cycle, that's usually when there's a lot going on, right? And there's a lot to learn if you want to learn it by heart, and you should be able to draw it by heart. That's the best way to learn it. If you want to focus on what you can remember from it, well, let's walk through it. Acetyl-CoA steps in, so it's a 2-carbon molecule with a CoA group right there, coenzyme A. And as I told you, as I alluded to in the first transition step, the first thing we do after harnessing, we harness the potential energy of the coenzyme A. So the coenzyme A is going to get out first thing in the cycle. And by having the CoA leaving, we are able to use that energy from that bond here. So that's the energy here. That energy is used, well, it's a weird bolt. That energy is used to get the final product of the Krebs cycle, which is called oxaloacetate. You don't need to learn the name, but if you learn that it's a 4 carbon molecule, that's essential because 4 in 2 gives you the first molecule that is 6 carbon. That's the first step, the citrate, the first step of the Krebs cycle, the citrate. There's some rearrangement becoming an isocitrate, but really here you want to focus on that first step to know the CoA bond is broken releasing the CoA, using that energy to attach the oxaloacetate to the acetyl to make citrate. That's your first step right here, right? So because we release carbon dioxide in the Krebs cycle, we now need to move on to that step. And remember what happened in a transition step when carbon dioxide was released? We were able to use the breaking of that bond of CO2 release to get some NAD plus with electron NH plus to make NADH for electron carrier. So that isocitrate here, which if you want to be fancy and know the terms, but you can also learn the carbon, 6 of them, you're going to go through one step that's going to be all about losing a carbon dioxide. And so remember, over here I'm showing only 6 carbons. They are OH and H's and O groups left and right, right? So you lose one, you go from 6 to 5. And when you do that, you break a bond, right? And the energy comes out of that bond here. Should I actually make the arrow in the same way as I did before? So that energy here is used in the process of shedding your carbon, which goes away with carbon with oxygen. So it's a carbon dioxide, CO2. That energy that's released here is used to do the really important work of getting NAD plus oxidized, plus H plus, oxidized to make NADH and the 2 electrons, right? So that's the first thing you do. And guess what? You do it again. The next step after that is another step in which you shed another carbon, and in that time you attach again hydrogen protons and electron to an NADH, NAD plus to make NADH, and another electron carrier. The only difference is that now you start from a 5 carbon and you go to a 4, so that's the next step. Now the 5 carbon is on top, you go to a 4, but you do something on top of all that, because remember, every time there's a reaction, there's some loss of energy. Previously, from isocitrate to the alpha ketoglutarate, that is the name of that 5 carbon molecule, you were not doing anything with that leftover energy. In that next step, when you go from 5 to 4 to shed another carbon dioxide, you do something with it. And what you do is you attach a coenzyme group, a CoA, to that carbon, to that chain. So now you have CoA here. So it's not using all of the leftover energy, but some of it. So the first, remember, you start from 6 carbons, you go to 5. So you go to 5 in which you release CO2 and you make NADH. Then from 5 you go to 4 and you release again CO2 and you make again NADH. In that case you attach CoA, right? So that's where the carbon dioxide are coming from, those 2 carbon dioxide here that we did back to back. Why 4 carbon dioxide in the output? Simply because we have 2 acetyl-CoA. So remember that everything I do here is double, because you go through the cycle twice since you come from transition step with 2 acetyl-CoA. Okay, so now you go from that 4 molecule of carbon with the acetyl-CoA. So now you have your 4. Lovely bird. And that CoA, and you go from that, and then you start harnessing a different form of energy in the process of shedding that CoA. And that's literally, you want to see of that attachment of CoA and shedding it right away as kind of a freebie. Because in that process, you don't lose carbon, you just lose a CoA. And the fact that you lose the CoA will release some energy that can be right away used to get ATP. Let's respect the colors a little bit. So that CoA goes away. And we get ADP plus P into ATP. And so really our carbon molecule has been changed slightly. So if you want to think about names, you go from succinyl-CoA to succinate, succinyl-CoA to succinate. But really the key was to use that potential energy in that bond here to shed the CoA that's releasing the energy that is here, to get that ATP molecule. Remember, you double that because you have two acetyl-CoA coming in the cycle initially, so you get with two succinyl-CoA, you go to two succinate because you go two cycle every time, and you have like so two ATP. Therefore, we have two ATP in the output. Now that we have a succinate here, the next steps are all about making more. It's all focusing on making more electron carrier, both FADH2 and NADH. So let's get through that. So we have our succinate 4 carbon molecule. The first thing we do to it is blink. We're just going to get electrons out of it. So remember that that molecule, although it's still 4 carbons, we shed over things that are around. Once again, if you want to know the details, go and check out that drawing from a previous student who actually drew it, or you can just go and Google exactly all the different bonds around that molecule, because I'm only showing you the core carbons here. But in this case here, we get FAD plus 2H plus, and we make FADH2. Don't forget the little electrons. So once again, we double that because we have two acetyl-CoA coming in the cycle, in the Krebs cycle, so we do twice that cycle. So that's why you have two FADH2, right? So far, we've done twice the NADH, so we still have to do it once more because remember, the output of the Krebs cycle is 6 NADH, and we have done 2 so far in one cycle, so since we do twice the cycle, we need to do 3, right? In order to do that, that's when the next steps comes in. Here, starting with that fumarate, which is the name of the molecule after you rearrange it by that reaction, we're going to input some water in it, and I'm going to do it all in once, that step here, although it's shown in twice. There's the malate step. But that carbon backbone doesn't change, but we're going to input some water in it to actually get it ready for that last NAD plus H plus to harness that energy coming from the water, right, that you input it. As soon as you add some molecule in the mix, that molecule is adding potential energy, right? Although you don't change the number of carbon, you change the number of bonds around because you add that water. And so you add some potential energy that can be harnessed to make NADH. And here you have it, you are back to the start of the cycle when you have your oxaloacetate, which is the name of the last molecule in the cycle that is bound to the acetyl-CoA in the first step I showed you earlier, thanks to the release of a coenzyme A that's giving you some energy to attach that 4-carbon molecule to the acetyl that's a 2-carbon molecule. And now that we've done 3 times that process of NAD plus H plus giving birth, like yielding NADH, we now have done it 3 times. We can know now that it's, since we go through the cycle twice, that's how we match the 6 NADH. So really, if you, like, I want to emphasize that really clearly. If you learn the output of every of those steps, when you draw it, it's informing you. If you know you need 6 NADH and you start with 1 acetyl-CoA, you know that everything you do, you're going to double it. So you know you have 3 NAD plus H plus 2 NADH steps. You know you need 2 ATP, so you know you have 1 ATP steps per reaction. And you know you need 2 FADH2, and so that you know that in the one cycle of the Krebs cycle, you have 1 step when you do that, FAD plus 2H plus FADH2. You know you have 4 carbon dioxide as output, so you know you're going to shed twice a carbon from that 6-carbon molecule that you start with after attaching oxaloacetate to acetyl-CoA, right? So hopefully you can do that drawing yourself until you learn it and you actually know it. That will be extremely helpful. Now we will switch to the electron transport chain, which is what do we do with all those electron carrier, FADH2 and NADH, sorry. So we'll see that next time. You guys take care.